Good almost afternoon, everybody. Next week, we will hear from Andrew Luisi, who, although he is information security officer for the campus, he has become he has a hobby, which is the history of computers, and he's going to add to our knowledge about what was happening about 50 or 60 years ago. And that's next week. Today, before I introduce today's speaker, I wanted to tell you that, as some of you know, that I'm advocating for teaching quantum mechanics to kindergarten students. And the reason for that is that if we get visited by ET, extraterrestrials, we will be toast. Guaranteed. But in the meantime, let's find out what quantum computing is all about. And our speaker today, Dr. Chubb from the University of San Francisco, will explain very interesting things like entanglement, superposition, spooky effects at a distance. So pay attention, even though you're not in kindergarten. Let's welcome our speaker.
Thank you for the nice introduction, and thanks for inviting me. Before I start, I have to begin with a disclaimer. This is not my research area, and it's a more and more serious hobby every year. But my background, I do have a background in physics, but my doctoral training and everything is, I'm really a logician, and I study, I study computability theory, which on the west coast of the US, I'm not really sure why people still call it recursion theory. I think it's political with something in Chicago. But, so what we study in computability theory is kind of like what you could in principle do with computers, right? Maybe you've heard of the halting problem, things like that. This is where computability theory kind of begins. So the halting problem is one of your first unsolvable problems. And in computability theory, what we do is take unsolvable problems and rank them according to how unsolvable they are, which sounds like a ridiculous endeavor, and I suppose, it kind of is, but it is fun. And one of the things that I study the most is computable structure theory, where we look at mathematical structures that are nice and sort of presentable, things like graphs, where you can tell if two nodes are connected or not in an effective way. And then think about other stuff that you would like to know about them, like maybe the distance between two nodes. And if you just know the edge relation, like how hard is it to compute distance, things like that. So that's really my research area. But I came to quantum computing some years ago and was attracted to it because, I did have a background in physics, and quantum physics was really always my favorite. I think probably because I'm not a physicist. I'm a mathematician, right? I'm trained as a mathematician, and doing quantum mechanics feels very much like doing axiomatic mathematics because you don't have any physical intuition about it at all. Just believe the postulates of quantum mechanics and do the math, and then do an experiment and see that magically it's correct, right? Your predictions. So that and together with so I loved quantum mechanics. I also worked in experimental physics for a while and did a lot of code writing to do data acquisition and stuff. So I like algorithms, and complexity of algorithms and things like that. So looking towards, looking into quantum computing I think it's a very natural place for me to have a hobby. And I'm going to tell you about some things about it today. So if I want to start by just trying to motivate this, like why are we even thinking about talking about quantum computing? I mean, after all, we've got really good computers, and maybe besides that, if the aliens come, they'll annihilate us, right? We don't have a choice. I don't know, is this font big enough? Can you guys see in the back? You can read this? Right, so Moore's law, if you're familiar with it, says that the amount of, the number of really transistors on a chip, it doubles about every 2 years, right? That's what Moore's law says. And you can see all graphs from this talk are swiped from the internet, so I just blanket cite my source for pictures, most of the pictures. But you can see, right, if you look at the development of these different processors, that it's actually pretty close to following Moore's law exactly. It doubles every 2 years. So this is a logarithmic scale. It looks like it's linear growth, but it's on a logarithmic scale, so that tells us it's exponential growth. Now I say it has a physical upper bound because when you start making things smaller and smaller, they can only get so much smaller until you're actually at an atomic level, and you can't ignore the effects of quantum mechanics, right? You can't ignore these laws that are, really have a big impact on small systems. This is another picture, that's right. This is another picture of Moore's law, which I thought was interesting too, because this is about calculations per second per $1,000, right? So calculations per second per $1,000, and it goes back to 1900, where we had, actual mechanical things, right? So there's an analytical engine down here, I guess maybe Babbage's kind of stuff, right? And things like, let's see, the Apple II is right here, and the Pentium processors up here. This line right here is mouse brain, right? So, I guess maybe the $1,000 doesn't really make a lot of sense when you're talking about how many computations you could do with $1,000 worth of mice, but I think the idea is that this is the number of calculations per second that a mouse brain can do, and you can see we're there. We're just about there. But where do we go next? Well, if the trend continues, we go up here, right? And this other line here, I don't know if you can read this, it says human brain. So this is the number of computations per second in a human brain, or $1,000 worth of human brains. And this little arrow here is pointing to things like quantum computing and DNA computing, and has a question mark, because really, what do we know? Well, I'll tell you some things about what we know. Anyway, so this is one reason, we don't have a choice. If Moore's law is to be believed, we're going to get there. We're going to get to super small things that we have to, deal with quantum mechanics. Right? And moreover, right, there is no such thing as classical computing. There's nothing classical in the world. The world is quantum. Right? What we're doing is trying to model classical algorithms with quantum systems when we build a regular old computer. Everything is quantum. There's no getting away from that. But we build our machines so that they kind of fight this quantum noise. And I think that you can make an argument for, instead of trying to wrangle a quantum system into something that looks classical, that we can understand very intuitively as classical beings, we should take advantage of this. We should embrace it and use the people call it the quantum weirdness of these systems to do things that classical machines can't do. And I guess last, I would say, as far as motivation for this, is the following. So you may be aware that there is probably not a quantum computer on your desktop, right? There's a huge engineering problem happening. And there's nothing in the theory that really seems to limit us in terms of what should be possible. But if we find that we actually can't do it for some reason, that reason will be a new part of physics. So it's kind of a win-win, right? We study quantum mechanics, we study these algorithms are fascinating and tell us that we can do things that classical machines can't do. And that's not to say that we can solve problems that are not solvable in the sense of unlimited time and unbounded time and resources. So you're not making, let's say you're not making the halting problem solvable with a quantum computer, but you can make things more efficient with a quantum computer and do things that you can't do with a classical computer. But if we run into a wall, that wall is going to be fantastic information that's going to maybe cause a paradigm shift in physics. Okay, so that's enough, I guess, for motivation for now. So I thought that since I'm going to do a little bit of calculating and take you through one of these algorithms, that maybe I should do that at the beginning when everybody's a little bit more awake. And then I'll show pictures and talk about history and people and stuff at the end when everybody's ready to fall asleep. Okay, fair enough? All right, so to just get our foot in the door and start with the very most basic thing, I think that it's useful to kind of build up the, the kind of nuts and bolts in parallel with the classical systems that we're all familiar with. So starting at the very bottom, right, you have bits, your binary digits. A bit is either going to be a 0 or a 1. And that's it. And for legal reasons, we're going to write that like this. So if we have a bit that's in state 0, we're going to write it like that. If we have a bit that's in state 1, we're going to write it like that. Right? Has anybody taken any quantum mechanics here? Okay. All right, so, and this is all classical, right? So now if we have 2 bits next to each other, if we're that lucky, we can actually use those 2 bits to represent 4 different things, right? Because the first bit might hold a 0, and the second bit might hold a 0, or 0, 1, 1, 0, or 1, 1, right? These are more commonly known as the numbers 0, 1, 2, and 3. Yes? Okay. So these are the, the basic building blocks of the tiniest part of, I guess, storage in a classical computer. In quantum computing, we have this sort of weird phenomenon that can happen that's called superposition, right? So just, accept this. Just believe the math, trust it, and everything kind of comes out okay. They can do this. That's something else, right? They can do this. But I'm not an engineer, so I can't really tell you very much about how. All right, so a quantum bit, right, a qubit, can exist in a superposition, which is just a fancy word for a linear combination of 0 and 1 at the same time. I'm saying linear combination. How many people had linear algebra? Like vectors and linear independence and stuff. Okay. So you know this word, right? Linear combination of 0 and 1 at the same time. So something like this, right? I mean, a single bit is going to look like a 0 or 1, but a qubit can look like this. It can hold this in memory. So this is just a linear combination of state 0 and state 1. I have this coefficient out front, 1 over the square root of 2. You can imagine distributing this, so it's really like 1 over square root of 2 times 0 plus 1 over square root of 2 times 1. That's your linear combination. Okay? I'll say something about 1 over square root of 2 in a minute, but if you like to just ignore the coefficients, that is also fine. Legal reasons, Right, so I put this on here because of this poster that I don't know how far around that was distributed. But, so the coefficient I have here for each of 0 and 1 is 1 over the square root of 2. But in fact, the coefficients need not be real numbers. They can be complex numbers. And in fact, they're often written this way. So this is cosine theta times 0 plus e to the I phi times sine theta. That I is not like an integer that you get to fill in, a variable. That's actually the square root of minus 1. So we're using complex coefficients in these. So I put this one up so I can show you this picture of the block sphere that was on this poster. So if you see, this is like a sphere, right, in 3 dimensions, and that blue arrow is intended to represent the state 0. So a classical bit could be in that state, represented by that blue arrow, or in this one state, represented by the red arrow. A quantum bit can be anywhere on the surface of this sphere. Okay. So when you want to plot it, you can always rewrite any qubit in this form so that you have a theta and a phi, and you can describe where that vector is by using, it's basically circular coordinates, if you remember that from, or a spherical coordinate system, if you remember that from calculus, maybe, yeah. And this is the unit sphere, so just the radius is all 1. Anyway, I just thought I would mention that but we don't have to do any complex numbers today. All our coefficients will be real, so don't panic. All right, and so this idea of having a qubit as a superposition of things that look like classical bits can be extended to strings of qubits. So if you have 2 qubits next to each other, you can actually write this as a linear combination. You can achieve a linear combination of all possible different scenarios, classical scenarios that are accessible by a classical computer. Now, I'll point out again, this is parentheses, right? You could distribute this, and then you'd have a coefficient in 1/2 in front of each of those 4 basic states, is what I call them. All right. So here's here's the mysterious thing about qubits, right? We have this fancy idea that they can exist in this superposition of 0 and 1 at the same time somehow, right? Like this. But the weird thing is that we never actually get to see this. We can never see this. If you look at a qubit, the only thing you will ever see is a 0 or a 1. Right? And here I wrote down there's a 50-50 chance of seeing a 0 or a 1, and that's true for this particular state. When we look at this notation and write our state as a linear combination of these basic states, when we make a measurement, we say the system collapses into one of the two basic states. The probability that it collapses into this state is equal to the square of the coefficient. Right? So the coefficient of 0 here is 1 over square root of 2. If you square that, that's 1/2. That's the probability that you'll see a 0 if you measure this. The coefficient of 1 is also 1 over square root of 2. Right? You square that, that's 1/2. The probability of seeing 1 is also 50%. Okay so far? I can't believe that's okay with anybody. All right, so, we've got this. Like, you can experimentally deduce that things can be in a superposition, things can be in a superposition, but you can't ever actually see that. Okay, so I think that really a decent strategy, and it's hard to try and explain quantum computing. It's just hard. It's a hard topic. But I think it's not so hard to walk through an example of an algorithm. Algorithms are the things that I think are really exciting because because I work in the theory of algorithms, and these are really weird algorithms. All right, so what we're going to do is see an algorithm to solve a dumb problem. All right, this problem is actually famous, although it is kind of dumb. The idea is that you have a function. Maybe I'll write. I don't think I put this on the slide, so maybe I'll just write. We're going to have a function. We're going to call it f. F is going to take a bit. It's either a 0 or a 1, and it's going to output either a 0 or 1. Maybe I'll just abuse notation a little bit and say its input can be 0 or 1, and its output can be 0 or 1. Right? So there are exactly 4 such functions. Right? One maps both 0 and 1 to 0. One maps both 0 and 1 to 1. Those would be the examples of constant functions. And then there are the other two. One is a bit flip and one is the identity. Those words all okay for everybody? All right. Then I won't write them down. But there are exactly 4 such functions. All right, so here's the problem. Someone is going to give us there it is, black box. And this black box is like a fancy kind of version of such a function. It's gonna just compute the value of the function for us. So I'll write it in kind of the general form first and then show you an example. So the idea is that time flows, information flows left to right. We're going to input 2 bits, right, one on each of these wires, and then 2 things are going to come out. The top wire, the top bit that goes in doesn't get changed. It's just left alone. So whatever you put in the top stays the same. In the bottom, though, we're going to get this weird thing. So this says the bottom bit, and then I don't know if you can see this, O plus is how I read that. It's really just mod 2 addition. Okay. And f of b1 there. So just a quick example. If I input 0 to both of these, then on the top, on the other side, out will come 0 because nothing changes. And on the bottom, we'd get 0 plus O plus f of 0. Right? So this would just be equal to f of 0. Right? So if I input a 0 on the bottom bit, it's like it's just making space for the value of the function. Right? It's keeping track of what was input, and it's making a place to write the output. You can think of it that way. Does that make sense? Give me a nod. You don't have to say anything. Just nod. Okay, so then here's the problem, right? Somebody gives you this box and says, can you tell if the function is constant or not? Right? So again, there's only 4 functions. 2 are constant, two are not. The non-constant ones are the identity and the bit flip. Oh, I think I wrote that down, yeah. So constant means that f of 0 equals f of 1, and not constant means that they're different. All right, so I'd take a moment to think about how you would do this, right? What would you do? You compute the value of 0, you compute the value on 1, and then you compare them, right? So you need to use that black box twice. Right? You need to use it to compute f of 0, and you need to use it to compute f of 1, and then you compare. In quantum computing, you can get away with only using it once. So just to practice with our notation a little bit, I'm going to just walk through the classical solution, right? You input 0, 0 to your box, and as we saw, out it's going to come 0 and f of 0. You get another copy of the box and put 1 and 0, right? Input ancillary bit. And the top doesn't change, and then the output gives you f of 1, and then you compare them. You can do it with an O plus, right? If f of 0 equals f of 1, what will be f of 0 O plus f of 1? It's either 0 plus 0 or 1 plus 1. What's that going to be? 0, right? In both cases, it's going to be 0. And if they're different, in either case, whether it's the identity function or a bit flip, you're going to get a 1, right? So we'll just do an O plus to compare. All right, so we used the black box twice. This is the naive algorithm, and I don't know, if you can come up with a better one that only uses the box once classically, then you better start writing your dissertation. It could be just 1 page long, maybe. All right, so now let's talk about the quantum solution. So this is the classical solution, right? The quantum solution uses this trick called the Hadamard gate. So you know how in computer science you have logical gates like negation, right? That's the bit flip, and you have ones that are kind of what I call them is non-reversible, right? Conjunction and disjunction, right? And or and things like this. So there is this gate called the Hadamard gate that's a quantum gate. And it does something that, you kind of need to be able to do if you're going to have some sort of controlled quantum scenario. It takes a classical bit, which is easy to prepare. You run this Hadamard gate on it, and out comes this superposition of 0 and 1. All right? Now, this is 1 over square root of 2, 0 plus 1, right? Just the same state that we saw before, this kind of the easiest state that's non-trivial. It's sort of a toy example. Now, if you give the Hadamard gate a classical 1, right, also easy to prepare, you run the Hadamard gate, you get almost exactly the same thing. The only difference is the sign in the center. If you think for a minute about what you might see if you looked at a qubit that's in this state, the probability of seeing 0 is 50%. The probability of seeing 1 is also 50%, right? It's not minus 50% because the minus gets squared along with the 1 over square root of 2. So, those two states to classical beings are indistinguishable. But the way that they work inside these machines and algorithms, they're different, and it's important. Okay, so here's another nifty thing about the Hadamard gate. If you give the Hadamard gate a qubit that's in this superposition, it will give you back the 0, right, that you put in. So it's its own inverse, right? It's its own inverse. It's completely reversible, takes you right back to what you started with. And the same is true with the with this qubit. So you can take a 1, do this Hadamard transformation, you always get this state, do it again, you'll always get back to 1. It is a good trick. All right, so here's the quantum solution. So, all right, so before I start clicking through this slide, everybody take a deep breath. Maybe stretch your arms out a little bit because, oh God, get ready. It's it's the nicest, cleanest example, but it's still a little bit hairy. So now's the time to kind of wake up. For me too. All right, so this is the circuit. Again, information flows left to right. We're going to have two inputs. They're going to be 0 and 1. We're going to run a Hadamard transformation on both of them, then run the result through the UF gate that we were looking at before. And then we do a Hadamard transformation, but just on the top one. And then we'll see what happens. Okay, so top and bottom wire are 0 and 1. I don't want to try and, you can't actually, because of entanglement, really write everything all separated onto two wires like that. So I'm going to write this like this. All right, so this says 0, this is not O plus, it is O times. It's a tensor product. So this is 0 tensor 1. We separate, if we can, the top and bottom wire with a tensor symbol. But I don't want to write that symbol over and over again. So when it's convenient and easily understood, I'm going to write this like this. Right? So the first thing is the top wire, the second thing is the bottom wire. Okay? So 0, 1 is what we start with if you were going to take a cross-section of the circuit at that moment. Now, what happens when we do the Hadamard transformation? Well, these are running in parallel, right? So this Hadamard gate is going to do the transformation on 0, and this one's going to do the transformation on 1, and we're going to get this, right? So this is the, I pulled out the 1 over square root of 2's, they're out front, but you can just ignore all the coefficients. They're all the same. So we get the 0 plus 1 in that top wire, tensor the 0 minus 1 in the bottom wire. And, just like what you guess should be true is true mathematically. Physically, nonsense. But mathematically, you think, oh, no, I could just FOIL this out. And in fact, you can, right? So this, I can just FOIL across this tensor product and write this state of this combined system at this moment, just like this. Check for a minute that my multiplication is correct. It's correct. I hope. My husband says, I shouldn't say things like that because he says, don't praise the day before the evening. It's like don't count your chickens, All right, so let's, before we try and do this next step, let's think about a particular example. So I want to try this. Suppose that we have a function. So we're in this state now, right? We're in the superposition of these four things. Suppose we have the function where f of 0 equals 1 and f of 1 equals 0. So is this one a little, can you see that better than the pink? Can you see the blue? Yeah. That's okay. All right, so this function I want to look at is this one, f of 0 equals 1 and f of 1 equals 0. Right? If that's the function that we have, what is the UF gate going to do to it? Right? So UF, remember, it takes in a B1 and a B2. It outputs that B1 and then it outputs B2 O plus f of B1. So I just wrote this down for reference. So let's think about, just go through this piece by piece. What happens if I put 0, 0 into the UF gate for this f? So I put 0, 0 in here. Out comes 0 on top, and what comes out on the bottom? 0 plus 1, right? So it'll be 1. So if I put in 0, 0, out comes, what do we say, 0, 1? Yeah, okay. And if I put in 0, 1, that's the next one in this expansion, right? If I put in 0, 1, so 0, 1, then I get f of 0, so it's still 0 in the top, but this time I'll get 1 plus f of 0, which is 1, so I'll get 0, right? So this goes to 0. And then if I do 1, 0, what do I get? 0. No, I have to get a 1 in the top, but in the bottom I get 0, right? Because it's 1 plus 1, right? B2. Wait, let's check. So 1 and 0, so if it's 0 and yes, okay. So it's 0 plus 0, right? And then 1, 1 gives me 1 and 1. Yeah? Okay, so it seems, oops. it seems almost too easy that you can look at this expression and try to do this quantum weird thing to it, but you can. You just go through term by term, right? What happens? And that's the result. This is a little bit small, I think, but it's if you just took this expansion and replaced this input with the corresponding output, this is what you get. It's exactly the same. Okay, so the next one is the one I really don't want to write down. I just don't want to show you yet because it's upsetting. So let me write this down because I didn't do this with the example. So we've got now, after that transformation, after the UF gate with this particular example, right, we have our system in this state. So it's 0, 1, minus 0, 0, plus 1, 1, minus 1, 0. Okay. Now let's just be brave and let's try and factor. I'm going to factor that second qubit out. So I'm going to rewrite this in a different order so it becomes a little bit easier. So I'm going to write this as 0, 1 plus 1, 1 minus, say, 0, 0 plus 1, 0. Okay, is that legible? All right, so it's just like factoring, right? Tensor product is just like factoring, except it's not commutative. I mean, it's like multiplication, but it's not commutative. So I'm going to factor a 1 out of the right-hand side of this. So I'll get, let's see, I'd get then 0 plus 1 tensor 1, right? So I can kind of pull that out. I can do the same thing in this other part. So I'll have, where's my pen? So I'll have minus, I guess, 0 plus 1. Let's see, minus 0 plus 1, completely lost my train of thought, tensor 0. Now you might notice that I have a 0 plus 1 and a 0 plus 1 in both places here. I can pull this apart. So I can factor out that superposition in the first wire. So I'll get 0 plus 1 tensor. This will be 1 minus 0. Now I suppose you know that if I pull out a negative sign, that'll be 0 minus 1, right? So I'll just make this minus 1/2. And then I've got 0 plus 1 tensor 0 minus 1. All right, so the top and bottom qubit are kind of separated now. And then we're going to take this next step with the Hadamard transformation. But let me catch us up in the general case to this point before we do that. Okay, so here's the idea. In the bottom qubit here, so you can see, right, this is a linear combination of two things, this and this. Each one of them is some representation of the two wires. Here's the tensor product. So in this part, this is the bottom wire, 0 minus 1. Also over here, in the bottom wire, this is 0 minus 1. 0 minus 1 is the superposition that's in the bottom wire. What's in the top wire depends on the function. All right, what's in the top wire depends on the function. So, so let's just check. Right, so imagine, maybe I did it. Did I do this in the next step? Because that would have been so smart. Yes, I did do it. Okay. So in the top, like if I factor this part of take the second wire out and just put it at the end, then I can see this is the superposition I have in the top. And the signs in the top they depend on the value of the function, right? So if f of 0 is equal to 1, like it was in this toy example, then you're going to get a negative coefficient in front of the 0. If it's equal to, and f of 1 then was equal to 0, so we get a positive coefficient in front of the 1, right? And, if they're both 0, then they're both positive. If they're both 1, they're both negative, and so on, right? So this is kind of where we are. Let me just check. Did the signs come out right here? Somehow I think I must have made a negative sign mistake. Right? So I have 0, so f of 0 was 1, right? So I should have a 0, I should have a negative 0 here.
Well, f of 1 is...
Yeah, but I did the factoring myself, right? So I lost track of something. You see this? Don't praise the day before the evening. Well, never mind. You can hunt for it later if you want to. All right, so we'll just remember that these are the correct signs. So let me just say again, right? If they're both the same, then both of these signs are the same. If they're both 1, then we get minus minus. If they're both 0, we get plus plus, right? If they're different, one will be positive and one will be negative. Yeah? All right. So constant functions, you get the same sign on both of them. Balanced functions, you get different signs on them. So what happens when you have something that, let me just see if I can back up to this. Oh, here it is. When you have a qubit that's in a superposition where both coefficients are positive, or if you like both coefficients are negative, just pull the negative out, you're going to square everything anyway. You have both signs the same on 0 and 1 and do a Hadamard gate, you get a 0. If you have the signs different and you do the Hadamard gate, you're going to get a 1. So that's where we are if we go back to the end of this, right? If the signs are the same, when you do that last Hadamard gate, you're going to get a 0. It's going to be a 0 in that wire. And if the signs are different, right, so if the function's not constant, then the signs will be different. And when you do that last Hadamard gate, you're going to get a 1. So you measure and you find out if you get a 0 or a 1. If it's 0, it's constant. If it's 1, it's balanced, right? And there's no probability about this answer. It is a correct answer, right? It's not. Some other quantum algorithms are inherently got a little probabilistic component to them. All right, so any questions? Right, again, the punchline, right, the trick, the thing that's the point here is that we can do something with quantum computing that you cannot do classically. You cannot figure out if this function is constant or not without using this gate twice. You just can't, right? But you can do it with a quantum computer. I should ask if there are questions. Did I already ask that? So then, of course, there's this question, right? This is a completely idiotic problem. Why would anybody want to build anything like spend $1 billion to build something like this to tell if some, 1-bit function is constant or not? Nobody cares about that. But there are quantum algorithms for doing things that people do care about. And they're far, far, and sometimes provably more efficient than classical algorithms. But, right, we don't often get a chance to make use of them. And we certainly don't get a chance to make use of them in any kind of practical way yet. So now we're done with all the calculations and we can just look at pictures and, the hard part is over. How much time do I have? I'm supposed to be done in 5 minutes? Yeah? I might be able to do that. Might be 6. Okay. All right, so where does this all come from? I mean, there are ideas about quantum logic and quantum information that go back They go back, I mean, if you really kind of want to reach back into the late 30s when quantum mechanics was starting to be developed, already then Birkhoff and von Neumann were thinking about what quantum logic might be like. And then there was some work in the 70s in quantum information theory, and I don't really know very much about that stuff, but it was in the very beginning of the 1980s that Feynman, at least in the West, is credited usually with the, sort of proposing that we start to explore this idea of a computer that takes advantage of quantum principles, mainly because it's just not feasible. It's not feasible to try and simulate a quantum system on a classical machine. It's not feasible. So I put this, so in the West, I said, right, Feynman is usually credited with this. Yuri Manin, though, you may know his name, right, lots of you, I think, published a paper in 1980, actually, in Russian, that was actually probably the first time this was proposed, but there was a little bit of an East-West thing going on in the early 80s, so not a lot of people in the West knew what was going on. Scientifically, the communities were sort of separate. Anyway, then what happens next, right? Well, then these two guys, well, there's four guys there, but I'm talking about that guy. I couldn't find a picture of him by himself, but that's I think his first name is Paul Benioff. Does anybody know Paul Benioff? He showed that you can build a quantum system that can model a Turing machine. Okay, right, like that was an important thing to do. That was an important thing to do. You guys know what Turing machines are? Yeah, okay. This guy, David Deutsch, who's a bit of a weirdo, he was actually the first person that in 1985, he wrote this paper where he talked a lot about the Church-Turing thesis and then proved that there is such a thing as a quantum, a universal machine, a programmable quantum machine. So, I mean, it's like, not actually realized, of course, but it's like the analog of a Turing machine, but in this quantum realm. He also is the one that gave us the only thing that we have that is any kind of programming language that's widely used for quantum computing algorithms, which are these kinds of logical circuits that I've already seen a few of, right? Let's see, I think this is a teleportation protocol or something. No, this is something that produces, it takes 3 zeros as inputs. These are controlled NOT gates, controlled NOT, yeah. And two more, this is all Hadamard transformations. But the end result here is in these 3 wires, it's 0, 0, 0 plus 1, 1, 1 over the square root of 2. This is what we call an entangled state. So when you have an entangled state, it's not possible to do, so those are the definition, right, it's a state where it's not possible to factor out the top and bottom wire separately. So you can't write this state as a tensor product. And that's where a lot of the algorithms in quantum computing kind of get their magic, is by taking advantage of not only superposition, but entanglement. There's somebody else, right? Oh yeah, right, so we go on. In 1992, Deutsch and Joza, I guess the problem that we just saw was called Deutsch's problem. The algorithm that we used to solve it is something that Deutsch and Joza are kind of jointly attributed with, to determine whether a function is balanced, that is the same number of 0 outputs as 1 outputs, or constant. And you can do this, you can generalize to n qubits, and usually we like 2 to the n qubits, but you guys probably like that too, right? 2 to the n bits, right? Yeah. All right. So, but that algorithm showed that quantum computers can do things that classical computers can't, right? You can get away with just using that gate once. In fact, even if you have 2 to the n, bits going in, right? You would need to, let's see, half of that. So 2 to the n minus 1 plus 1 would be the number of times you'd have to check on a classical machine, but you can still get away with just one. So that's exponential speed up, right? exponential speed up with the Deutsch-Jozsa algorithm. Simon's periodicity algorithm, which is used to find the period of some periodic function, again a binary function on some string of qubits, can find the period. So if you frame this problem the way that they did in 1993, it can find the period of this function exponentially. That's provably exponentially faster than any classical algorithm. And Grover's search algorithm is one of the first ones that is kind of like, people care about this problem, searching a database. This is something you can like take whole courses in probably, right, is looking at databases. And so Grover's search algorithm, which was published in 1996, is an algorithm that has quadratic speed up over a classical machine. And then, of course, the very famous Shor's factoring algorithm in 1994, which really was the thing that happened that invited a lot of attention to quantum computing. I think a lot of people thought, these were, people that were studying quantum computing were like the same people that said that they've been abducted by UFOs. But once they saw, right, that you can factor numbers exponentially faster than any known classical algorithm, this really got everybody's attention, and I suppose that you know why without me telling you. That's mean if there's somebody that doesn't know. So it's because of encryption, right? A lot of encryption relies on this problem of factoring big numbers being hard and taking a long time to do. But Shor's algorithm can do it fast. It's a complicated algorithm, but it's really, really cool if you take the time to study a little bit of number theory and something called the quantum Fourier transform. It's a really cool algorithm, beyond the scope of this talk. All right, so now, of course, like we have this idea of what it is, at least in a toy setting, right, mathematically. It's natural to wonder, where are we with this, right? So I've said some things about the theoretical developments that, they were kind of, like if you think about the history of computer science, which maybe, I guess, after next week's lecture is about the history of computer science. Is that what you? Well, yeah, but it's from, is it going to be like the 30s?
60 years ago.
Oh, okay, all right. So the stuff this history that I've just given with the David Deutsch's work and all this stuff, it's like what Turing and Church were doing, right, in the 30s and 40s. Implementation is another thing. Right? So that's physics and engineering, really. So in 1998, the very first 2-qubit nuclear magnetic resonance computers were realized, and 3 bits later on. But this was the first quantum computer. Now, we call these quantum computers, but I got to say that really every single one of them is built for a very specific purpose. There is no programmable one, right? So that's a very, very different thing. There's no universal quantum machine that's been realized. In 1998, let's see, Grover's search algorithm, so this is searching the database, was executed on a computer like this. Of course, these are really, really tiny computers, so you can't do very much. In the year 2000, a 5-qubit machine was realized in Munich and a 7-qubit machine at Los Alamos National Lab. And then finally in 2001, Shor's algorithm was executed on a quantum computer for the first time. And it doesn't sound very impressive, but it was a very big, expensive deal that they factored 15 at Stanford. And by 2005, they had a string of 8 qubits in Austria, 12 qubits in Canada. In 2006, you can see it's growing and growing, right? And then, okay, so in 2008, you guys have heard about D-Wave systems, maybe, because Google bought them and all this stuff. It's very sketchy stuff. So they claim they had a 128 qubit machine in 2008, but didn't, kept everything proprietary and didn't share. Around 2012, they did publish an article, and I think Scott Aronson went to visit their facility and came away feeling more positive about D-Wave, but has since become, less generous in his discussion of their work. I know, I'm being recorded, so now I'm getting nervous about what I say. All right, so in 2011, they factored 21, and then 143. That's huge, right? 3 digits. They needed 4 qubits. But to see like what kind of engineering problem we're actually looking at, these things have to be cold and they have to be really, really isolated. It wasn't until 4 years ago now, I guess, that a 2-qubit machine was actually able to function at room temperature. And even then, it could only work for 2 seconds. And that's because this decoherence happens. These are extremely vulnerable to any kind of contact with the outside world. It's just going to turn them right into classical systems, just like when you look at a qubit with a microscope, the entanglement, the superposition, it's all ruined if they're disturbed by an outside system. All right, so 2014, the number 56,153 was factored, and I think this is the most recent development, and I mean, maybe it doesn't sound like a quantum computing thing, but teleportation, there is a quantum computing type protocol for that, and they were able to teleport a quantum state 101 kilometers, which is a big deal, right? That's far, and they have also been able to maintain entanglement for 6 hours. Now that is not at room temperature. It's not at room temperature. But that's kind of, I don't know, that's kind of what we're coming up to. It's really, we're making progress. We're making progress when you think we went from 2 qubits in 1998 to being able to, teleport 101 kilometers away. All right, so, oh yes, what's next, right? So of course, like I've just been saying, there's this implementation problem, right? Entanglement is hard to maintain. It's even hard to achieve. And there's this big engineering problem and maybe even like a physics problem. Oh boy, I talked way longer than 5 minutes. This is my last one. There's also programming, right? So we have only a handful of algorithms. I literally have listed every single one. There are other algorithms, but they all kind of have at their heart one of these. I don't remember if it was 4 or 5 different things. The Deutsch-Jozsa algorithm, Simon's periodicity algorithm, the Grover's search algorithm, and the quantum Fourier transform from Shor's algorithm. Why are there so few, right? Why haven't we found more of them? Maybe it's just because we don't have the right intuition for it, but we, it's a strange phenomenon. We also don't have any kind of notion of what a programming language would look like, but that really comes down to quantum logic, I think, and there are lots of people thinking about that. Right, so of course, classical logic is Boolean, right, and truth tables and stuff. There's lots of people thinking about quantum logic and how, what kind of logic should underlie these quantum algorithms. And then there's all this stuff, right, information transfer protocols and error correcting codes and cryptography and secure money. All of this stuff has people in quantum physics interested. And I meant to put this picture of this book last. It's a shameless promotion because it just came out this year. But what I wanted to show you was this picture. This is a picture of a, I can't remember how many qubits it is, but this is one of the first quantum computers to execute the teleportation protocol. And they managed to do it over about 1 meter of space in a lab. So when you think about where we are with this, so this was about 10 years ago. This is, I think it's like 2 or 3 qubits. Right? That's what it looks like. So we're a long way from getting lots and lots of transistors on a chip, right? We're at a different place. We're at the beginning. Anyway, thank you very much for coming.